Okay, so I hope that that was a good video for you to watch. He really explains Cavendish's experiment and also again then goes over those graphs. So I thought he was quite knowledgeable and that he explained that well, so I thought that that would be good for you to watch. Also, like, you know, if you are confused with something in class, YouTube it, because there's lots of other teachers that are putting their lessons on YouTube, and it might just help you to have somebody explain something in a different way. Okay, so now we are going to do some examples to for this law. Oh, also, like with Cavendish's experiment, that's something that you need to be able to explain and do yourself. So, yeah. So, okay. So now, calculate the magnitude of weight. Okay. So weight, remember, is Fg, right? Still the weight due to gravity of a 6.5 times 10 to the kilogram spacecraft. That is 4.15 times 10 to the 6 meters above Earth's surface. So just to kind of give you a reference, if this is Earth, this is the radius of Earth. But then it said this spacecraft is above Earth. So it's like I'm going to put my spacecraft in a different color. So here, if I had my spacecraft is above Earth's surface, so then that's an extra radius. So I'm going to put R of my spacecraft there. And I'm calculating the magnitude of the weight of the spacecraft. So I need to find out the entire distance between my two objects. So this is going from like the core of Earth to the actual spaceship. So I'm going to say that that's my RT. So R subscript T. Alright. Okay, so let's write down everything that we have here now. So M1 I'm going to say is 6.5 times 10 to the 2 kilograms. And now I have also, M2 is going to be my ME, which is our mass of our Earth. So go to your data booklet and look at mass of Earth, which is 5.97 times 10 to the 24 kilograms. Now I'm going to have my R total is equal to my RE plus RS. So RT then is equal to 4.15 times 10 to the 6 meters, because that's how far away the spaceship is, plus my RE, which I get off of my data booklet. So that's 6.37 times 10 to the power of 6 meters. So then my RT, what I can actually use in my formula when I add those two values, is 1.052 times 10 to the power of 7 meters. Okay, so now I can plug this stuff into my actual formula. So I have Fg is equal to G times M1 times M2 over R squared. Remember to square your R. So Fg is equal to, and my big G is my constant, which is again in my data booklet, so this needs to be pretty handy. 6.67 times 10 to the power of negative 11 times 6.5 times 10 to the 2 kilograms times by 5.97 times 10 to the 24. Sorry, I'm running out of room there. Okay, I'll rewrite it for you. Lots of numbers in these ones. So all divided by my RT, I'm going to use my RT, which is squared. So now, if you're putting this all into your calculator at once, I would recommend that you need to put all of this that's on your top of your fraction into brackets, divided by your bottom. So when you put that into your calculator, which I want everyone to try right now, make sure you do that, you should get 2.34 times 10 to the 3 newtons. Okay, again, if I go too fast or anything, you can just ask sub to pause. Okay, how much would a 60 kilogram person weigh on Mercury if Mercury has a radius of 2.51 times 10 to the 6 meters and a mass of 3.28 times 10 to the 23 kilograms? Okay, so I am looking for Fg, the person's weight, which is Fg, force due to gravity. R, I'm told, is 2.51 times 10 to the 6 meters. Mass 1, I'm going to say is the person, is 60 kilograms. It doesn't matter which one you choose as M1 or M2, it's going to be the same. Same value as your answer. And mass 2 will be my planet, which is 3.28 times 10 to the 23 kilograms. So my formula is Fg is equal to G times M1 times M2 divided by R squared. So let's plug that all in. Oh, I'm going to back up a bit just because I know this top line is a lot of writing. So 6.67 times 10 to the negative 11 times by 3.28 times 10 to the 23 times by 60 kilograms. All of that is divided by 2.51 times 10 to the 6 meters, and that value needs to be squared. So plug that into your calculator and you should get 208 newtons. Oh, and also, so we're thinking about this is Mercury, so from here to here, this is the radius of Mercury. The person is standing right on Mercury, so there's no extra radius that you need to add on to it. It's just the radius of Mercury. So it's different than like our first one where we had to find RT. This one you just take the radius of the planet or object if the other object is directly on top of it. Okay, now we'll move into our last example.